Freefall consists of all unsupported objects near the Earth's surface that fall towards the Earth with the same acceleration. We call that the acceleration due to gravity and is denoted by g. And g, the magnitude of g, is 9.8 meters per second squared. So that should always be a positive. If you see g in an equation, replace it with 9.8 meters per second squared. But you might say you see it with a negative sign all the time. Okay, so let's talk about that here. Just to reiterate, all objects, regardless of mass, accelerate downward towards the Earth at the same rate, the same acceleration. G is a constant. It does not change near the surface of the Earth. If you go higher, like on huge mountains or up in the space shuttle, it decreases a bit, but we're not going to worry about that here. The hopper is not going to go that far. Now here's where the negative sign comes in. Since the acceleration is downward, we consider the acceleration negative. So A will equal minus g, which is minus 9.8 meters per second squared. So don't go and put another minus in for g, because then you'll get a minus, minus, and that'll give you plus. You don't want that. So the acceleration is negative, but the magnitude of g is positive. Let's illustrate what it means to be in free fall. Now we're going to throw an object up with initial velocity v0. Now for the experiment, we're really just going to throw it up straight, so it should come right down in the same path. But we've kind of expanded this here so you can see the different points when it goes up and when it comes down. So the first question, what happens when it goes up in terms of acceleration and velocity? That's this piece here. What happens at the very top? What happens when it goes down? And what happens right before it lands? The answers to these will be on the next slide. So here we go on our little journey, and just to remind you again, for the hopper, it's going straight up and coming straight down. So we throw the object upwards with an initial velocity v0. On the way up, the velocity starts slowing down, and the acceleration is negative g, which is negative 9.8 meters per second squared. So that's telling us when the velocity is in one direction and the acceleration is in the other, you're slowing down. Just like if you're driving a car and you hit the brakes, you're still going forward, but the acceleration is backwards. It's in the other direction. Right at the top, you actually stop momentarily. So your velocity at the top is 0. We'll be using that. And look at this. The acceleration is still the same. The Earth is still there attracting the object. Now we start coming down. You speed up again, right? You slow down going up till 0, and then you sped up. And in this case, we still have a is equal to minus g. But the velocity is in the same direction as the acceleration, so you speed up. Again, just like in a car. When you hit the accelerator pedal, you go faster. You're accelerating in the same direction you're moving. Then right at the bottom, right before you hit the ground, you have the negative of the initial velocity. So it's the same magnitude, the same speed, just in a different direction. Here's a special case. If an object is launched from the ground and returns to the ground, the same height, which basically is 0, then the time to the top, and we're going to call that the apex, is half of the time it takes to go all the way to the bottom. So it would take half the time getting up and half the time getting down. And one more time to remind you, it's not really going like this. We're throwing it straight up and it's coming straight down for this problem. This is going to be a shortcut we can use where we don't know the initial or final velocity. Here's what this looks like on a graph. So we're throwing the object straight up in the air and then it comes down and hits the ground again. So what is our graph here? It is a velocity time graph. You always read the y-axis first. And you start with a certain velocity. Let's just count the marks. It looks like 3. So we have a velocity of 3 meters per second, for example. And that's the initial velocity v0. From a couple slides ago, we said immediately it starts slowing down. And it slows down in a linear fashion. So you can see the velocity, hopefully, slowing down until you get to a certain time, and here we say that time is, let's call that 3 seconds. So it stops momentarily, so the velocity is 0 there, because on the t-axis v is equal to 0. Now you can take the slope of that line, and the slope is what? Rise over run, so that would be v over t. Well, what is that? That's a definition of acceleration. So it's a negative slope, and actually the value would be negative 9.8 meters per second squared. So that, of course, doesn't fit with what I said for what these values are, but don't worry about that. The slope of the line will be negative 9.8. Then why do we have a negative velocity here? Well, that meant the object went all the way up, hit the peak right there, and then started coming down. So that's a negative velocity. And it finishes, and let's see, when it finally hits the ground, it has the same velocity as what it started, the same magnitude of velocity, it's just in a different direction.